live. Yeah, and let's wait a minute. No, I'm just checking whether Professor Makinde is in the attendees. Otherwise, Professor, how you pronounce your surname?
Egunjobi.
Egunjobi. Okay, Egunjobi. I was one. Yeah. I thought maybe it's no Egunjobi. Egunjobi. Okay. Ah, here we go. I found him. He's in the audience. Okay. Okay, he should be with us now.
All right.
Ah, here we go. Hello, Professor Makinde. How are you? Can you hear us?
Yes, hello.
Ah, hello. How are you? Good afternoon.
Yes.
We are already live because you ended up in the participants, and I had to fish you out of the participants and make you a panelist.
For the past 30 minutes, I've been trying to come in.
I know. It's sometimes it can be too much. So, yeah. But since we are all here, I think we can start. And Professor Egunjobi, he has also joined us, and I will ask him just now to introduce you and to moderate the question at the end of the talk. Yeah. So let's start. So good afternoon, everyone. Welcome to this edition of the NITheP Colloquium on a load-shedded Monday afternoon. So thank you very much. If you have to make some special arrangements with power banks and UPSs to be with us, that's really much appreciated. Today's speaker is Professor Makinde from the University of Stellenbosch, the Faculty of Military Science, and he's an expert in applied and computational mathematics. Yeah, and with us on the panel is also Professor Egunjobi, who is a professor at the Namibia University of Science and Technology, and he's joining us from Windhoek this afternoon. and I will ask him just now to introduce Professor Makinde. And on the panel is also Professor Sinaisky from UKZN, who is our standard co-host, just in case I have problem with ESCOM or the internet. Ilya has all the rights to keep going with the webinar. Yeah, that's so Ilya is the plan B. Yeah. So Professor Egunjobi, may I ask you please to introduce Professor Makinde to our audience this afternoon?
Thank you, and you are welcome. Good afternoon, everyone. Thank you for being here this afternoon. Today, we are pleased to welcome Professor Oluwole Daniel Makinde, a very special guest from the Faculty of Military Science, Stellenbosch University, South Africa. By the way, before I go far, my name is Professor Aditayo Samuel Egunjobi. I'm from Namibia University of Science and Technology, Windhoek, Namibia. So Professor Oluwole Daniel Makinde is a professor of applied and computational mathematics at the Faculty of Military Science, Stellenbosch University, South Africa. He is also a visiting professor to several other universities. These include Adama Science and Technology University in Ethiopia, Africa University of Science and Technology in Nigeria, a Valor Institute of Technology in India. Before joining Faculty of Military Science, Stellenbosch University, Professor Makinde already worked as a senior professor and director of postgraduate study and the founding director of the Institute for Advanced Research in Mathematical Modeling and Computations at the Cape Peninsula University of Technology, South Africa, between 2008 to 2013. and a full professor and head of applied mathematics department at the University of Limpopo, South Africa, between 1998 and 2008. Professor Makinde is a recipient of a 2014 Nigeria National Award, Honor Award, titled the Member of the Order of the Federal Republic, MFR, for his outstanding contribution to mathematical science and technology in Africa by His Excellency, the President of Nigeria. He is the winner of the prestigious 2011-2015 Africa Union Kwame Nkrumah Continental Scientific Award from Africa Head of State for outstanding contribution to basic science, technology, and innovation in Africa. The winner of South Africa National Science and Technology Forum and the National Research Funding, NRF 2009-2010, T.W. Kwambule Senior Researcher Award for outstanding contribution to science, engineering, technology, and innovation in South Africa. The winner of the Best Senior Research Scientist Award at the University of Limpopo from 1999 to 2007. The winner of the Best Senior Research Scientist Award at the Cape Peninsula University of Technology from 2008 to 2012. The winner of the 2014 and 2015 Highly Commendable Published Paper Award from Emerald Group Publishing, UK. The winner of the 2015 Most Outstanding Reviewer Award from Emerald Group Publishing, UK. The winner of the Research Scientist Award at the Faculty of Military Science, Stellenbosch University from 2016 to 2019, and the Stellenbosch University 2019 Chancellor Award winner for Outstanding Research Excellence. He also won several distinctions, scholarship, fellowship, prize, grant, and awards. Professor Makinde received a prestigious Fellows of the African Academy of Science, FAAX, for outstanding contribution to science, innovation, and technology in Africa, 2012. He was also awarded a Fellow of the International Academy of Physical Science, FIAPS, for his outstanding contribution to the field of mathematical science, 2018, and a Fellow of a Papua New Guinea Mathematical Society for outreach contribution, 2013, to the development of mathematical science research in Papua New Guinea. Professor Makinde is on the editorial board of several reputable academic journals, such as Journal of Applied Mathematics, Africa Mathematica, Journal of Nanofluid, Journal of Nigerian Mathematical Society, and Open Chemical Engineering Journal, PLOS1, etc., and also serve as a reviewer for many reputable international academic journals worldwide, and for the NRF. He is the lead guest editor of two special issues titled New Development in Fluid Mechanics and its Engineering Application, published in the journal Mathematical Problem in Engineering 2013, and the Nanofluid Flow and Heat Transfer, published in the journal Advances in Mathematical Physics 2014. In 2017, Professor Makinde edited two research books titled Advances in Nonlinear Heat Transfer in Fluid and Solid, Diffusion Foundation, Volume 11, and New Development for Heat Transfer in Solid and Fluid Flow, Diffusion, Defect and Diffusion Forum, Volume 377, published by Transtech Publication, Switzerland. In 2018, he also edited research book titled Fluid Mechanics and heat transfer in Applied Engineering Diffusion Foundation, volume 16, and computational analysis of heat transfer in fluid and solid, defect and diffusion forum, volume 387, published by Transtech Publication, Switzerland. Recently, in 2020, Professor Makinde edited another research textbook titled Engineering Fluid Flow and Heat Transfer Analysis, Diffusion, volume 26, and Computation and Solid 2, Defect and Diffusion Forum, volume 401. In addition, Professor Makinde authored 4 universities applying mathematics textbook and monograph, and published over 500 highly impacted research papers in several reputable international journals. As you can see, he has a, when you go to Google, you will see it's a metric there. It's a IH index is 60, citation index is 15,639, and I-10 index is a 316. He organized several conferences, workshops, and symposia within and outside Africa continent, and delivered keynote research papers at several national and international conferences and workshops worldwide. He has an extensive record of research and academic collaboration with several faculties and universities in countries such as Kenya, Ethiopia, Ghana, South Africa, Zimbabwe, Tanzania, Namibia, Botswana, India, Algeria, Iran, Pakistan, Germany, the United Kingdom, the USA, Saudi Arabia, Bangladesh, Papua New Guinea, and China. His research covers a broad range of topics, including fluid mechanics, nanofluid dynamics, heat and mass transfer, hydrodynamic stability, dynamical system, thermal science, combustion theory, biomathematics, and epidemiological modeling, computation mathematics, and improved perturbation techniques. His research in the area of computation mathematics has generated a new approach to tackling nonlinear problems that model real systems. The main objective of his research is to use mathematical theory and methodology to gain insight and biology of industrial, environmental, medical, and social interests. Professor Makinde research has contributed immensely to the upliftment of many scholars in the field of mathematical science research and postgraduate training. He has taught, supervised, and mentored several students at undergraduate, postgraduate, and postdoctoral level. I'm happen to be one of his students, and now I'm professor. And we have some of his students in South Africa there who are professors, and some of his students who are professors in Ghana, and some of his students who are professors in other countries such as Kenya, Tanzania, and so forth and so forth. So he has supervised over 37 PhDs, 73 MSc, and 200 BSc honor candidates in the field of applied mathematics and computational across Africa continent, and served in several high-level academic management and administrative positions. He is also served as external examiner for many universities within and outside the African continent. He is a certified member of the International Association of Engineers. Professor Makinde served as the Secretary General of the African Mathematical Union from 2009 to 2017, the Vice President and General Secretary of the Southern African Mathematical Science Association from 2020 to 2006, a founding academics advisory board member of the African Institute for Mathematical Science from 2003 to 2005, an associate member of the International Center for Theoretical Physics 2000 to 2005, and an associate member of the National Institute of Theoretical Physics in South Africa. And today, he will be sharing with us his expert opinion on the nanofluid dynamics and its engineering cooling application. With that, I ask you to give your full attention to Professor Oluwole Daniel Makinde and help me welcoming him to the stage. Now, Professor Makinde, can you help me, please? All of you, help me welcome Professor Makinde on the stage.
Yes,
Thank you very
thank
much.
you very much.
Thank you, Prof. You are welcome.
Thank you very much. Thank you very much, Professor Egunjobi. I'm highly delighted with your extensive introduction. I know I've worked with several people, and without wasting time, I will quickly go into my presentation so that at least it will, after that, we can have some discussion. So
yes, while you share your screen, I will quickly remind our participants to use the Q&A facility to ask questions so that Professor Egunjobi can moderate a session of at the end of your talk. So please, we can see your slide. Maybe if you want to press the full view button, you.
Yes, I will do that and see, because of the internet, to make it. If there will not be problem with the band. So let's continue. I think it's okay. Can we progress?
Perfect. Thank you very much.
Yeah. Okay, thank you very much. Let me first start by thanking God Almighty for giving me this opportunity to share opinion with colleagues. As you know, knowledge is not local. Knowledge is international. Therefore, I give glory to God in spite of all these COVID-19 and restrictions. We academics are still able to share knowledge, and we are alive by the grace of God. Thank you, and thank everyone who have made it to attend this presentation. So as you, let me also thank the organizer of this talk, the National Institute of Theoretical Physics, based in Stellenbosch. I thank you for inviting me and giving me this audience. Thank you very much. I know I've given several lectures in many countries here and there, but probably this will be an eye-opener for colleagues and also for students, postgraduate students, who we also want to engage in collaborations that will help them to see the type of thing we are doing. And as I said, my area of research, this is one part of my area of research, which is on fluid mechanics. Other part is mathematical biology and also computational mathematics. But today, we are dealing with the area of fluid mechanics, which is titled Nanofluid Dynamics and its engineering cooling applications. So that is the title of the talk for today. Now, let's go into the presentation overview. What I'm going to talk about will be as highlighted on the screen. The first one is introduction. Second part of it will be applications. Third is literature review, the fundamental equations. Then we have a model problem to look at, numerical approach we adopt, and the numerical result, conclusion, and references. And before I go further, you can see here, this is what we call nano liquid for all phones. So it's a kind of nano liquid. I will tell you what is called nano fluid. And what is a fluid? A fluid is anything that can flow. Fluid means flow. Anything that can flow is called fluid, which means the concept of fluid covers two major states of matters. You know, in state of matters, we have solid, liquid, and gas. So which means fluid dynamics covers two major parts, which is the liquid and gas. So even in solid state, solid in molten form can flow. So the fluid mechanics can even encroach into solid state. For instance, you know what we call magma. Magma is a molten rock that can erupt during the volcanic eruption. They flow before they become solidified, can be classified during the flow stage as a fluid. So it's a broad area, but I'm going to talk mainly on nanofluid today and its cooling application in engineering. And you can see here, this is a super nano coolant. It's used for cooling engine. And I will tell you the reason why. Why is nanofluid used for cooling, for electronics cooling, for engineering cooling? Because from the talk today, you'll be able to see clearly, even the cell phone, We use what we call nano liquid for cell phone, because every electronic generates heat, and therefore this heat needs to be dissipated, need to be removed. If the heat is not removed, those systems will not be reliable. They'll be damaged. They can be thermal away. Therefore, so the concept of nanofluid and the nanotechnology is extremely important in the engineering system of today. Now, let's go to what is nanofluid itself. Nanofluid is a mixture of base fluid and nanoparticles. You can see from the picture here, this is water, this is a fluid. Water is a liquid. This is a solid. Alumina is a solid. It's a powder. A powder cannot flow. Because a powder cannot flow, it is not a fluid. And this water can flow. Water is a fluid. But what is important is that when you look at some of the base fluid here, which I put here, oil, water, oil, and lubricants. Lubricants like oil, engine oil, and so on and so forth. You have ethylene glycol, you have polymer solution, biofluid like blood, and so on and so forth, plasma, and other common fluid. These materials, they can flow. Water can flow, oil can flow, ethylene glycol can flow, polymer solution can flow, biofluid, blood can flow, plasma in the blood can flow. They are liquid. Gas can flow. But the problem is this. When you want to cool a surface, you need something that can flow across the surface, which is fluid. But again, you need that fluid to have very high thermal conductivity. Because if the thermal conductivity of fluid is high, the rate of conducting heat out of the hot surface and transferring it away from the surface will be high. Unfortunately, this base fluid, which you have here, their thermal conductivity is very, very low compared to solid. Solid like metals, oxide ceramic, metal carbide, nitride, non-metallic like carbon nanotube, graphite, and so on and so forth, alumina, copper, and even what we have here, aluminum oxide, copper oxide, and so on and so forth, or copper, or iron oxide, all these things, they have very high thermal conductivity compared to fluid, compared to liquid or fluids. But the problem with them is that they cannot flow. Metal can't flow. If you place a metal on a surface, it will remain there. It will not flow. That's why it's high thermal conductivity. Water can flow. So because of that, what nanofluid does is to marry these two, husband and wife, the water and the metallic or non-metallic material. You marry them at laboratory condition, which means it is based on experimental observation. When these conventional fluids, when you put small quantity, for instance, this is 0.1% of alumina, if you mix it with water, it is observed that the thermal conductivity of this new liquid you have here is higher than that of ordinary water, which means this liquid now with 0.1% alumina can conduct it better, can take it out of the surface better than using conventional fluid. If you increase it to 1% and you mix it homogeneously under laboratory condition, we also observe that the rate of heat transfer, the thermal conductivity become higher, up to 1%. So you can see, although the color change, but the heat transfer capacity is enhanced. So that is what makes nanofluid to be a very advanced ultra heat transfer liquid or fluid being used in engineering system for engineering cooling nowadays. So, but the problem is this there, which I will emphasize as we move forward. Let's go to the next slide. In fact, from what I put here, this is a nanoparticle, which particle fabricated to 10 raised to power minus 9 meter. That's what we call nano size. The size of the particle is of this. It's just like very, very tiny powder in powdery form. That each particle is of size 10 raised to power minus 9. In engineering, there are many machines designed to fabricate and to produce nano size. You can also produce it through chemical reaction and so on and so forth. So production of nanoparticles of this can be done chemically, mechanically, and so on and so forth. But what I'm trying to put in this talk is to show you how we can model this and how to choose the best nanoparticle that can produce, that can enhance, mixed with the best liquid that can enhance the heat transfer, how to compare many particles with each other and see how it goes in terms of cooling. Okay, now the next one here is why nanofluid? I've already mentioned that. Conventional heat transfer fluid have poor thermal conductivity compared to solid. Rising in demand of emerging technology, for instance, we are now having what we call micro devices. Micro, like cell phone, they are micro devices. Devices are becoming smaller and they generate heat. So how do we take out the heat from the system to make sure that the system works better? That's number one question. Even some of our electronics, like refrigerator, like the air conditioning, everything generates heat. How do we start to deal with that? So those are the things. From the diagram here, you can see engine oil is number one. You can see ethylene glycol 2, water 3, alumina, silicon. As you increase from 1 to 9, you can see the thermal conductivity of the material increases. Here is liquid. As we are moving to number 4, you can see alumina, silicon, alumina, and so on and so forth. There is increase in thermal conductivity. And that is why mixture of these two, if you use only these, the transfer rate will be very, very small. So because of that, we have to go into issue of thermal nanofluid. What are the applications of nanofluid? Like I mentioned, this is one of the applications, electronic cooling. I've mentioned cell phone and all kinds of materials which generate heat. When you put nanofluid, which is a mixture of the base fluid and nanoparticle, it enhances the cooling by taking away the heat. Also, transportation cooling. You can see here automobile, aircraft, and so on and so forth. Most of these systems, they generate a lot of heat during operation. Like what you see here, the cooling of engine. That's why we have radiator. You put a kind of nano liquid in the radiator to make sure that the heat generated are being taken away. Otherwise, the engine heat can cause a kind of thermal runaway to the system. So also, when you are fabricating material, industrial cooling, you fabricate materials, you shape them, they're in liquid form to solidify them and take out the heat uniformly. You can use nano liquid or nanofluid in cooling. In military, you can see in military, most of the military equipment, they generate a lot of heat during operation. Nanofluid is used to make sure that the heat are being taken away. They are being removed from the system for effective operation during military operation. You also see here a nuclear reactor. We use nanofluid in cooling nuclear reactor because they generate a lot of heat. And when the heat is generated, if that heat are not taken away, then it becomes a big problem to the system. So nanoliquid are used or nanofluid in cooling nuclear reactors. there are several applications of engineering cooling on all these and engineering devices or industrial engineering devices which generate a lot of heat, which need to be cooled down for effective operation. Now, let's go to modeling of heat transfer in engineering system. As you know, when you want to model heat transfer in engineering system, there are two ways of dealing with the problem. That's what they call experimental and theoretical analysis. There are two major ways. Both ways are excellently good, but one of them is more expensive, whereas the other one is less expensive. And in these days that financially, there is a lot of problem in terms of financing a very big project through experiments. Therefore, theoretical analysis will be most important to get the system right before finance come into it. In fact, that forms the basic concept of National Institute of Theoretical Physics, where theoretical aspect is done before we can now go, so that you don't repeat the experiment several times. You already have idea of what is going to happen, so that when you do it once, you get it right, and the product can be produced. What are the experimental approach? It has advantage dealing with actual physical system, and the fair quantity is determined by measurement within the limit of experimental error. However, this approach is very expensive, time-consuming, and often impractical. For instance, you don't perform an experiment to go to the moon before you landed in the moon. You have to do theoretical model. You don't go to the moon because you don't know whether your system, your aircraft will carry you there. The theoretical approach has to be done, modeling has to be done before a prototype experiment is now designed. And everything is looked at under laboratory condition before you now go. But theory comes first. And that is what we have here. Also, some of the experiments, for instance, the nanoliquid, to fabricate nanoparticle is very, very expensive. In fact, there is a laboratory in the Temba lab under the supervision of Professor Malik Massa. Malik Massa is also doing some experimental work on nanofluid and nanoparticles, fabricating and producing nano and testing the applications and all those things. And they have those equipment they are using and extremely expensive. Extremely expensive. So therefore, not everybody can have access to that kind of expensive material to produce a nanoparticle and to test the applications and to see how useful they are. But there is a way out before experiment can be done, so that experiment is done well. And when you do experiment and you fail, millions of dollars have lost. You have to redo it again by buying the material again. But for theoretical approach, you don't waste any money except your computer, your software, and the knowledge. The only problem in theoretical is that one must have the right knowledge, right skill, both numerical and theoretical, to deal with the problem. So the theoretical approach has advantage that it is fast, it is inexpensive, but the result obtained are subject to accuracy of the assumption. That is approximation and idealization. You have to assume and you improve your assumption to reality, and you get the result. The more closer to the reality, the more complicated the problem becomes, the more mathematics you needed, the more numerical approach you needed to get the problem going and get this result. And once you get the result, you can now go into experiment and perform it, and it will confirm exactly what you have done. Then when you modify it, you'll be able to assert that, yes, we can now go into into production of the material. Now, modeling procedure. When you want to model in terms of theoretical, because my area of specialization is theoretical aspect, not experimental aspect. So in the modeling procedure, You have to follow these guidelines. You have the physical problem. In this case, we are talking of nanofluid. Then number two, you identify important variables. You want to see the dynamics of nanofluid and its engineering cooling application. That is the problem. You have to identify a physical problem. Then go into important variables that are involved. You have the nanoparticles, whether you have what you call the metallic or non-metallic nanoparticle and your base fluid. Those are the important variables, and the quantity of the nanoparticle you are using. You have to get them right. Those are the important variables. And the heat transfer you need to check, and the issue of skin friction, the effect of it on the surface also. Need to then make reasonable assumptions and approximation. Apply the relevant physical law. This is where you need the knowledge. When you are dealing with problems like this, you need to have absolute grasp of the concept of fluid mechanics. Fluid mechanics, which deals with the conservation law of energy, conservation law of momentum, conservation law of mass. You need to have it at your fingertips. And if there's any physical effect, like magnetic field and so on and so forth, and buoyancy, and you have to know all those physical effects as well. So you need physical laws. You need to be very fast in it. Then from there, you generate the differential equations. You may also, in most cases, it may not be a differential equation, it may be a stochastic differential equation, maybe a stochastic equation, maybe a discrete equation. Anything you can get as a model, depending on your area of expertise. Then you apply applicable solution techniques, numerical, analytical, you can do that based on your model. Then from there, you apply boundary condition and you get the solution. When you get a solution, then you can move back and improve your solution by adding more physical effect to it, get a new model, and continue like that. So these are the steps which I've highlighted. So for those who are research students, these are the ways to approach. You must make assumption and make sure that you stick to your assumption. And that will produce you the model. Model, what you call model is the equation. Whether the equation is stochastic or differential or deterministic or whatever you get, that form your model. You solve it, you get your solution, interpret your solution, then you go back, improve your model, and make it closer until you get to the real thing. Let's now go to the model, which talks about the dynamics. You can see when you are looking at cooling of hot surface, you can see here, this surface, this surface you have here, you are cooling this surface. What we do is that you put fluid flow towards the surface. As you put fluid on the surface, fluid can flow this way, flow that way. In that case, you are having what you call stagnation point flow. Because when fluid hits the surface, you get to a point here where the velocity is zero. There is continue to flow on the surface. But in fact, what you actually have here is what we call bandy layer flow. For instance, look at this surface here. This surface here, assuming it's hot, the fluid is flowing towards the surface. It hits this point. It started spreading around the surface. The fluid that is taking it of the fluid are those ones close to the surface. There is a thin region around the surface which interact with the surface. That thin region is called the bandy layer region. That's where the viscosity and the property of the fluid, that's where it varies. So we have to look at that. So you have to visualize the model and see how it is. You draw a schematic diagram. So that is very, very important. Now you move forward. Let me talk briefly about issue of bandy layer. When you cool a surface, you have to put fluid on top of a surface. Whether the surface is moving or stationary, you put a fluid on top of the surface to take out the heat. So when the fluid is flowing on the surface, you call it a bandy layer problem. Then you have thermal bandy layer problem, you have concentration bandy layer problem, you have a momentum bandy layer problem. When you put fluid on the surface, you have that. The first person to deal with this type of problem is a scientist called Prandtl. Prandtl is a scientist who tried to look at aerofoil, the aircraft's wing, how the wind blow, the air blow around the wing, how to have the wing that will resist, that will resist the effect, the drag, the effect of the air on the wing. So he was looking at it. And one of his students is Blasius. Blasius look at what we call Blasius band layer problem. This is a plate. A plate, we have a flat plate. You have a fluid flowing on the surface with velocity u. It's flowing on top of the surface, and the fluid is flowing. You can see the band layer profile. It goes like this, and this delta is the thickness of band layer. At this point, the velocity is 0 at the point of entrance. Because of this edge, when the fluid moves, the band layer side, that is the band layer region, which is described as a region where the viscosity of the fluid is affecting the surface. So that region continues to increase until you get to a point where you have the free stream, viscosity of fluid not be affected by the surface anymore. That is where you have this. The problem is that what is the thickness of the band layer? This data. We also want to know that what is the effect of the fluid flow on the surface? The effect definitely we know is called friction, which is called W, shear stress. There is a friction. The fluid is crashing the surface. So we want to know the effect of the fluid on the surface. We want to know the profile, velocity profile, thickness of the band layer. And when you have thermal band layer, I want to know the temperature profile within the band layer region. So all these are important. Now we are dealing with nanofluid, not ordinary fluid. Now look at this. Blasius did this. He was able to get similarity variable that convert the momentum equation. That's similarity variable derived by Blasius, which is what we call eta is y over delta. Delta here is band layer, size of band layer, which is of order inverse of the square root of Reynolds number. That is the band layer delta. The thickness is of order inverse of the square root of the Reynolds number, which we have here. Delta is of this order, and this is Reynolds number, so on and so forth. So Blasius deal with this, and you can get them in many textbooks. They are all available there. But this problem formed the basis of issue of engineering cooling, which is what I'm talking about now. Also, you can have the issue of aerofoil design, the issue of ship, those who are doing the Navy, the naval people, the engineers who are building ship, because you are moving within in the sea, in the river, in the sea. So you have to design it in the form that the wind and all the turbulent happen in the ocean will not be able to capsize the ship, and so on and so forth. Turbulent blade, turbine blade, and so on and so forth. So the concept of band layer, even the fan you have in your house, when the fan is blowing, it's moving round, is work on the concept of band layer. Again, this surface which you have here, you can have a slippery surface. If the surface is slippery, that is, if the surface is lubricated, it's slippery, then you have what you call no slip condition. You have this is slip condition. Slip condition means if the surface is slippery, it's not, or it's a smooth surface, you have a smooth surface, you have to apply this condition called the slip condition, which is called Navier slip condition. That is, the velocity of the fluid is proportional to the velocity gradient. So that is what you can use. But if there is no slip, that is, this surface is coarse, it's a coarse surface, then you can have what you call no slip condition. That means this part will be 0. On the surface, the velocity will be 0. Otherwise, you will have what you call slip condition. So all these can be looked at depending on the surface you are trying to cool, to look at the type of surface. Anyway, in terms of literature, the concept of nanofluid began with the work of Cho, 1995. Cho is an engineer. He was able to fabricate metallic materials. He fabricates in a form of, he make it a powdery form to nano size, and he mix it to the base fluid under laboratory condition. You see that there's no coagulation. That means they flow uniformly like homogeneous fluid. When you put small percentage, and you see that the heat transfer capacity of such fluid is highly enhanced compared to using the base fluid. In 1995, he performed experimental work on it, and he was able to show that by doing this, we can enhance the rate of cooling of engineering system experimentally. And thereafter, several scientists have worked theoretically and experimentally on different types of metallic and non-metallic material to make sure that in getting nanoparticle mixed with base fluid to see their different rates of heat transfer capacity, to see which one will give you better heat transfer enhancement rate compared to others. There's also a problem of stability of the nanofluid, because some metallic substance, they are unstable, they can be easily oxidized. If you use copper powder, copper can be oxidized to copper oxide. That means the thermophysical property of copper will decrease. Therefore, it will also affect the quality of the nanofluid, which we have initially, but it still be better. It is still better than use ordinary base fluid. So all this we are going to talk about and look about it. So several work has been done on the theoretical and so on, and I talk of the work of Cho 1995, the work of Cho 2009, and the work of the Eastman, Lee, and so on. They have done so many experimental work on different type of nanoparticle, and also get some empirical relationship between nanofluid, nanoparticle, and base fluid. All these were documented in the literature. Now, when you talk of binding layer, you have a surface that is moving. When you cool a surface can shrink, or when you cool a surface can be shrinking, or can be stressing, or can be fixed, can be stationary. That is, you can have a moving surface, you can have a fixed surface, you can have a shrinking surface that you are cooling, which is hot. So many people have worked on this type of thing. Like the work of psychiatrists, I've also done a lot of work on problem of stagnation, point flow, 2012, 2008, 2009. So many work has been done, 30 and so on and so forth. And so many other people have, even some of my students, like Prof. Sheini, in the head of engineering faculty in Ghana of University for Development Study. Prof. Sheini is the head of engineering faculty there. I mean, he's the dean of engineering faculty. He also work on nanofluid for his PhD under me, and so many other people. Ibrahim also is there in Ethiopia. He work with me on some of the work on nanofluid stagnation point, looking at the magnetic field impact, the issue of a non-Newtonian nanofluid. And so many work has been done. Let's go into the model now and the problem, into the dynamics. Like I said before, the foundation of fluid dynamics and the conservation law, specifically conservation of mass, conservation of linear momentum, also known as Newton's second law, conservation of energy, first law of thermodynamics, and also you can have these laws in classical mechanics. You can have them derived in classical mechanics or quantum mechanics and in form of general relativity. And you can derive them using Reynolds transport theorem. All these are the basic mathematics involved, or basic physics involved in the derivation of the mathematical equations. We found fundamental conservation law we are going to use. And other effects like buoyancy, magnetic field, porous media, and all those things, using Darcy law, using Maxwell law for electromagnetic, all these things has to be there, which are the physics aspect of the whole thing and their mathematical relationship. We have to look at that in getting model, whatever model you want to do. Now, let's look at the problem I want to talk about now. For nanofluid dynamics, here I'm using a single phase flow model, and I'm assuming an incompressible base fluid, which means density is constant. I'm using a Newtonian nanofluid. Newtonian nanofluid means the relationship between the stress and strain. The relationship is linear. When you have relationship between stress and strain, when they are linear, then you have what you call Navier-Stokes equation, which gives you the momentum equation for Newtonian for Newtonian fluid flow and incompressibility under the assumption of incompressibility fluid and the constant density. The only difference here is that the density here is density of nanofluid, not the density of base fluid. That's why I put rho NF This is the viscosity of nanofluid. This is pressure gradient that pushes the fluid. In this case, I can add, this is body force, because the nanofluid can be susceptible to magnetic field. Therefore, there is possibility, if there's flowing to magnetic field and is flowing under the action of magnetic field, we can add what we call Lorentz force. This is a Lorentz force, which we act on the flow of the fluid, on the velocity of the fluid. If you know in physics, we have the right hand principle. So you can see this Lorentz force, it can either oppose the movement of the fluid, or it can enhance it depending on where it is applied. Then we have the energy equation. This one is based on conservation of momentum, the conservation of energy from the first law of thermodynamics, which says that change in internal energy is equal to the work done on the system and the heat added or removed from the system. So from using that, you can get the energy equation. So you have this energy equation, and here you can have this one is the physical dissipation part, and you have this one is due to magnetic field. J here, which we have here, is the electric field. The current density. Sorry, J here is the current density. D here is magnetic field, and the expression for current density, which comes from Ohm's law, is given by this equation from Maxwell law of electromagnetism. These are Maxwell equations. You have J, where sigma here, which you have here, is your electrical conductivity, and that is sigma, which is electrical conductivity of nanofluid. This is electric field, and V is velocity vector. And you have Faraday law, where magnetic field changes, then you have electric field is produced. So you have the Faraday law and you have the Ampere's law. So all these are needed, and you must be, as a mathematician, one must be able to derive it. One must be able to know under what condition do we use this model or that model. Is the fluid Newtonian or non-Newtonian? This is just, I'm just showing you one area. Use a single phase flow model. You can also use two-phase flow model. In this case, we assume that the fluid, the base fluid, and the nanoparticle, they are homogeneous mixture and they flow uniformly together. Not that you have the two phases whereby the nanoparticle are flowing differently and the fluid is also moving differently. No, they move homogeneously. We have homogeneous mixture in this type of model. There is also a model which was derived by Boggiano, where you deal with an issue of two-phase flow. In that case, we are looking at thermophoresis and the Brownian motion effect. That will be our focus. And there's also a work I did recently, which was published in the Journal of Thermoanalysis and Calorimetry with my student, who also Dr. Monaledi. We published that work. It just appeared this year, 2021, where we combine both single phase and two phase to form one single model. In that case, the equation will not be like this, because the nanoparticle is now moving differently. So we generate those, we combine the two models to a single model, both Boggiano for two phase and single phase. You can check the literature. It was published. It's a very high H index, high H index journal, and a journal is part of the work one of my students, Dr. Monaledi, did for his PhD. He graduated in Stellenbosch this last December. And work has appeared this year. It's already published. You can look at it if you are interested. Now let's look at nanoparticles and base fluid properties. This information you have to get it from engineering textbooks. They are documented in literatures. You have material, for instance, for the one I'm considering here, you can see the density. Rho is the density. The density of water, pure water, copper, and alumina. This one is the specific heat at constant pressure of pure water, copper, and alumina. This one is thermal conductivity, K, for pure water, copper, and alumina. This one is the electrical conductivity of pure water, copper, and so all these, you need to get the value. what is the question? The question here is that if I mix copper with water, or I mix aluminum with water under laboratory condition, which one will transfer it better? Will I get high heat transfer compare than using ordinary water? You know, which one is the best? So we have done it for many materials, metallic or non-metallic, and compare with all the base fluid. It can be engine oil, it can be biofluid, it can be all kinds of things which we have used. And this just to showcase part of the work we have done. Several work has been done. Look at some of my papers. You see a lot of things there. Now, the other point I want to tell you is that when these nanoparticles you see can be fabricated in different shape. You can have nanoparticles that are spherical in shape. They are nano size, 10 to the power minus 9, but they are spherical in shape under microscope. You can look at it. You can have a brick shape, you can have a cylinder shape, platelet shape, disc shape. This is their sphericity. The sphericity of each of the shape of nanoparticles is given, and the shape factor, the shape parameter m, is 3 over psi, which is given. So when m is 3, in terms of their thermal conductivity, if m is 3 here, then you have a spherical shape nanoparticles. Now, if you divide m by 0.81, you have a block shape, and so on and so forth. You can have different shape. This gives you a relationship between the nanofluid and the base fluid. You can see here, this one tells you the density of nanofluid. When you see NF, nanofluid, F means base fluid, S means nanoparticle. Phi here is the volume fraction, the quantity of nanoparticle we are using. If phi here is 0, if phi is 0, that means you don't have nanoparticle, you only have base fluid. Rho NF will be rho F. If phi is 0.1, that means you have 10% of nanoparticle in the base fluid. If phi is 0.01, you have only 1%. So we are going to look at different percentage of nanoparticle. In fact, in practice, you don't use more than 10% of nanoparticles to get that, because the more you can see phi is 1. Look at the viscosity of nanofluid. As you are increasing phi, the viscosity of nanofluid is increasing. And all these relationships are empirical relationship obtained through experiments. And this is the thermal conductivity of nanofluid, and this sigma F is that of base fluid, and you can sigma S is that of nanoparticles. And you can see all these are needed, which we have to put in our equation. So if you use the equation I have here, let's go to the model problem and see. We want to model this problem. You have fluid, nanofluid being poured on this all surface, and the surface here is stressing. The surface is stressing, and you have fluid poured on this surface. This surface is shrinking. Now, we want to know what is the effect of nanofluid on the shrinking surface. What is the effect of nanofluid on the stressing surface? Which one can take it more? What is the cooling rate of the stressing surface or shrinking surface, or where the surface is fixed? Based on what I've shown you, the dynamics of nanofluid equations, the fluid dynamics of nanofluid equations which we have there, we derive these similarity equations. This equation is the model similarity equation for this problem, where M here is the effect of magnetic field parameter. The assumption made is the fluid is steady flow, two-dimensional, incompressible. And this is a coolant poured on the surface to take out the heat from the surface. And the fluid is flowing this way and is under the action of magnetic field. What is the effect of magnetic field on it? This is the temperature equation. Theta here represents dimensionless temperature, where F represents dimensionless stream function, where derivative of F is the velocity of the fluid. So this is the similarity equation we have, and this one is that of the temperature, the energy. From energy equation, you get this one. From the momentum equation, you obtain these similarity equations. And these are the boundary conditions. We assume the surface here it can be slippery. If the surface is slippery, then S here will not be 0. If the surface is stressing, lambda here will be positive. If solid is shrinking, lambda is negative. If lambda is 0, S is 0, that means the surface is stationary and it's a quartz surface. So you can look at different actions taking place here. For temperature, DI is called the thermal bout number. It tells you the rate of heat transfer, the rate at which heat that is generated under here. This heat here can be due to chemical reaction, can be due to electronics, the electronics operation, generating heat, and you are cooling it here by taking out the heat from the surface. So the rate of heat going, the rate at which heat is being taken, is going through this material and is taken away by the nanofluid on top. That rate is called bout number. The convective heat transfer from the material here, generated heat from the hot fluid here to the other surface, to the upper surface, through this wall, through this sheet. It's called the bout number. So increase in BI means that you are increasing the bout number, and so on and so forth. So if this always generating heat and it's increasing, we want this one to be taken away the heat so that the heat is not accumulated, otherwise there will be explosion. The same thing for this material. When the heat is generated, what can we do? We want to take out the heat for shrinking surface. Now we have got the model. This equation we have here are called model. We turn the PD to ODE, we get this one. But this equation, you cannot just solve them easily by finding the exact solution, because this equation you have here, they are non-linear. Although there are ways of solving it, you can form exact, there's a way of getting exact solution to this one. I was able to get approximate solution to this. In fact, one can see how to obtain some kind of exact solution to this problem. But again, in generality, these are non-linear problems. You can see F, this squared, F multiplying each other. This one is squared. You can see here, you can see you are squaring this, you are squaring. So these are highly non-linear problems. And this is still very simple. There are models which are done where the equation is even more highly non-linear than this one. Where you have buoyancy term, you have issue of porous media and everything involved. Now, when you get this equation and you have the boundary condition, these are the boundary conditions. This is the free stream. Free stream is called infinity. At infinity here, you have this velocity, uniform. And temperature at infinity is uniform. But within the boundary layer here, this is where we want to know what effect of what is happening here to the surface. Within the boundary layer, we want to know the momentum boundary layer thickness, the thermal boundary layer thickness, and the skin friction and Nusselt number.
Prof.
Okay.
Prof.
Sorry,
yes, sir. They said that we should conclude everything before 5:15.
Okay. I will move very fast now. Thank you. So these are the similarity variable used. You have BI, theta, and so on, so have to define. This is the Prandtl number, Icard number, Bout number, and so on and so forth. So these are the similarity. This is the one nanoparticle volume fraction slip. So I mean the slip parameter and so on. Now you can see here, this is skin friction. And this one is Nusselt number. This one is heat transfer enhancement rate. This one, when phi is not 0, that means there's no nanoparticle. I mean, there is nanoparticle. When phi is not 0, when phi is 0, no nanoparticle. So you want to compare what is the heat transfer rate when there is nanoparticle and when there is no nanoparticle. You want to look at the percentage increase in heat transfer. So we have to calculate this and compare them from using different nanoparticles and see which one is the best. And also what is the effect on the surface, which is the skin friction, and what is the heat transfer rate generally, which is the Nusselt number at the hot surface. So these are the things we do. To solve the problem, you can solve the problem using many numerical methods. You can use finite element method, finite difference method. You can use it depends. You can use homotopy analysis method. And you can use a perturbation method based on homotopy perturbation. There are many methods to solve this and get approximate result. And the approximate result can be more accurate. For in this case, I use shooting method based on Runge-Kutta of order 4, which is, I can call it Runge-Kutta-Fehlberg method. That is, you turn the boundary value problem to initial value problem. And you now integrate it using NITheP to get the unknown initial condition, which are what we have the unknown initial condition, and this is A1 and A2. And you now solve the problem as if it's initial value problem, which is called shooting techniques. And it's very, very accurate because the Runge-Kutta we are using is of high order accuracy. And we are using NITheP also to get the unknown initial condition. So these are the things we do there. Okay, let's look at the results. The results are as follows. When you do the computation, this is copper water, this iron oxide water, this aluminum oxide water. And these are the graphs we have here. What you notice is that for shrinking, when you have a shrinking sheet, when the surface is shrinking, we observe there is possibility of dual solution. That's when lambda is negative. There is a dual solution in the range of lambda, between lambda, which you have here, which is around minus 1.3 to minus 1.1 or something, 1.2 here. There are dual, there is solution here, these are dual solution. So which is very, very interesting. Although it's a nonlinear problem, we expect to have multiple solutions. But for shrinking sheet, we have dual solution. And in the dual solution, one of them will be the right solution, the other one will be a solution that is not, you can't get through experiment. So in fact, one of the things you can see here is that when you use copper water, the lambda, which you get is minus 1.274, which means the surface will shrink more. The shrinking rate of the surface will be more when you use copper water as your nanofluid. And the shrinking will be less when you use alumina water as your nanofluid. This minus 1.2, you can see. That's one of the important results here. But for all of them, we see that there's a dual solution because of the shrinking of the surface, where we have a lower solution branch and upper solution branch. And we also see from what we observe here is that when you now take copper water as our working fluid, the same thing applies to iron oxide and water and aluminum water. You can see here, if you increase nanoparticle using copper water, if you increase nanoparticle, zero means no nanoparticle. Zero here is when you have zero is where you have blue. Where you have black here is where you have 10%. 0.1 means 10% of nanoparticle. As you increase the nanoparticle, the shrinking rate of the surface also increase. You still have a dual solution. The dotted line means the lower branch of the solution, where the thick line means the upper branch. But out of this branch for shrinking surface, we need to know which one is correct, which one is incorrect in terms of experiment, because in the experiment, which one can you get? You can't get two solutions for a single problem. On the experimental analysis, you only get one. So we have to do the stability analysis of the aerodynamic stability analysis of the lower branch and upper branch, which we did. And we're able to show that the upper branch is stable and is physically realizable in other experiment, and the lower branch is unstable. As we increase as we increase the percentage of nanoparticle, the skin friction increases. That's what you see here. The effect of the fluid on the surface in damaging the fluid, the effect increases also with increase in nanoparticle from 0 to 10%. You can see increase in skin friction. Also, we look at slippery. You can see you have 0.1 and you have this. You have 0.4. You can see when lambda is 0.1, the rate of shrinking as the surface becomes more slippery, the rate of shrinking also increases. Increase in slippery rate means increase in the shrinking, rate of the surface. That's what you observe. Although there's still dual solution. Also for magnetic field. as we increase the intensity of magnetic field on the fluid, the skin friction also increases. You can see M is 0.1 to 0. As we increase skin friction intensity, you can see the increase in the skin effect of the fluid on the surface. Here we put our nanoparticle to be 0.1, we fix nanoparticle to be 10%. And stripping rate is constant. We are just changing one parameter, which is magnetic field. As we are increasing the intensity of magnetic field, you can see the increase in the skin friction because the fluid get close to the surface and they brush the surface more and more. That is what this is telling us. Meanwhile, it also enhances because if the fluid get close to the surface, it slows down the rate of flow of the fluid gets close to the surface, it takes more heat from the surface. That means fluid pushed to the surface, it takes more heat, but it also affects the surface because of the increase in skin friction. And the shrinking rate, you can see the shrinking rate also increase for where you have but for stressy surface, you only have a unique solution. A solution is only unique. You can see from 0. 0 is where the surface is not moving. And when you go above 0 here, 0.1, 0.2, and so on and so forth, you only have a single solution. It's not dual. Even for some part of the shrinking, when it's negative lambda, you also have a single. It's only for some range where dual solution exists. This one are obtained through the mathematical analysis and numerical consideration of the flow of the problem, which are part of the mathematical solution, but the physical solution is the thick one, which you only get under experiment. So these are the things. Increase magnetic, increase shrinking. Then we also look at, like I told you, we want to look at which solution is right, which one is in the issue of shrinking. When you have dual solution, we perform the hydrodynamic stability of the results. This is our basic flow. The basic flow here is where the flow is steady. We perturb the flow by adding this time-dependent perturbation, disturbance. And this disturbance which you have here is very, very small. Beta here is called the eigenvalue. For those who are aware of the hydrodynamic stability, they will know what I'm trying to do here. So we regenerate the equation. We got the eigenvalue problem. This eigenvalue problem. What is our aim here? Our aim is to find beta. Beta here is the eigenvalue. Remember, if beta here is negative, is positive, we solve this beta based on these boundary conditions. We solve this eigenvalue problem based on the boundary condition numerically. If beta is negative, then put beta negative here. That means if beta is negative, the negative then becomes positive. As tau, which is the time, tau is the dimensionless time. As time increases, this disturbance will become bigger. This is what you are seeing here. So now it becomes bigger. It's growing. So now it becomes bigger. It's growing. Then beta negative, which means the basic solution will not no more be a basic solution. You cannot get this solution. Disturbance we make, we amplify the disturbances. I mean, the disturbance is amplified when beta is negative. But when beta is positive, then as t goes to infinity, this time will go to 0. You will recover back your basic solution. So that is what will determine which one is whether the upper branch is the true solution or the lower branch is true solution. So we solve the problem for beta. You can see the eigenvalue, the smallest eigenvalue here for the beta. You can see it's positive for upper branch, which means beta is positive. As if you disturb this basic flow, as increases, big time increases, this one will go to 0, you recover back your solution, which is what is happening here. Solution become your basic flow. So this one is realistic. But you can see here for lower branch, the smallest eigenvalue there is negative, which means if you disturb it, as you increase time, this disturbance will grow. You will not recover your solution. That is the problem we have there. So the true solution of the experiment is the upper solution branch. We're able to get that. Then when you thought of heat transfer, the heat transfer enhancement rate, we were able to see the blue one is copper. copper water, alumina water, ferrous oxide, iron oxide. You can see that if you put the 10% volume fraction inside water of copper, alumina, and iron oxide for different nanofluid, you can see the one with copper will give you a very high heat transfer rate. Heat transfer enhancement, the cooling rate of copper water will be extremely high. Copper water will take more heat from the surface compared to alumina and iron oxide water. So the nanofluid made up of copper water is the best when you compare these three, followed by that of in terms of cooling of the surface. When you compare, the second one is the ferrous oxide, followed by alumina oxide, which is the third one. This is what you can see, which will obtain through. Then you can compare others also and see, follow the same principle and see. We also see here that as you are increasing the percentage of nanoparticles from 1% to 10%, using ferrous oxide, using copper, using alumina, the rate of the transfer rate increases. That is the transfer enhancement rate compared to water. They are increasing. That's what you see here. And you can see the reason why copper water is the best is because copper, but this copper water is not stable because copper is a metallic nanoparticle you are using. It can oxidize easily. But this one, alumina water and the ferrous water, they are stable. This nanoparticle for alumina, they are stable. But the copper water is okay, but it's not stable because it can undergo chemical reaction and the chemical composition of thermophysical property of copper changes. Anyway, we have different, because of the time, you have all these numerical results, which I've already explained and so on. But let me go to conclusion. Nanofluid velocity increase from the wall towards the free, to the free stream. Velocity boundary layer thickness of alumina water nanofluid is greater than the one of copper water. Velocity boundary layer thickness decreases with this parameter which I've mentioned, which is sleep parameter, magnetic field, the strictly of stressing rate, and also nanoparticles and so on. So all these, the imperative is that dual solution exists for streaking sheets. When you are cooling a streaking sheet, the surface is shrinking, then you have dual solution. But the upper solution branch is your resolution of the experiment. And we also say skin friction increases when you increase magnetic field and the nanoparticle volume fraction you use. But decreases when there is a skin, when the surface is polished, that is, when you have a lubricating surface. When the surface is lubricated, S. When you have X, S decreases skin friction. Surface. And also, when you increase lambda through stressing, when someone is stressing, then you can see that the rate of the skin friction is also reduced. All these are solutions we obtain. Then we'll talk of heat transfer enhancement. You see nanoparticle enhance heat transfer, and it also enhance heat transfer enhancement rates increased by nanoparticle. Bout number also increase transfer enhancement rate at the same time as stressing and so on and so forth. Whereas, you can see these are what we have for Nusselt number, which I have shown in the transfer enhancement rate. Finally, to enhance the cooling rate at heated surface using nanofluid, it is advisable to regulate the value of various embedded parameters with respect to engineering and industrial application. So this parameter that is involved need to be regulated to desired result. If you are using any nanofluid and you have to regulate the bout number, you have to regulate the Eckert number, and all this can be regulated through engineering design to make sure that you get desired result for your nanofluid. So that's one of the important results here. Although generally, there's a general result that nanoparticle in the base fluid enhance cooling rate by increasing the transfer enhancement rate. So this is what we have done so many work, and let me stop there for questions because I think the time is fast approaching. Thank you very much. I thank everybody for giving me the audience, and God will be with you all in Jesus' name. So that's it. Question time.
Thank you. Thank you, Prof. Thank you, Prof. Thank you for taking your time. Thank you for sharing your your experience with us on the nanofluid. Thank you for telling us the why nanofluid. Thank you for telling us the application of a nanofluid and the experimental and theoretical aspect of a nanofluid. I have one question on the chat here for you, and that person is asking, any comparison with the experimental results?
Yeah, thank you very much. There are a lot of comparison with experimental results. Let me cite an example. There was a paper I published with Professor Malik Massa at the Temba Lab. Was it in 2018, where they had to look at issue of sliver ethnic glycol kind of nanofluid. And then in that paper, it was published in the material science, in the material science journal. And we were able to compare what they obtained through experimental results. They are doing experiments. I include issue of this kind of model to it, and but not this particular one, the one that deals with issue of heat transfer. I went to show them that, look, what we are obtaining through this model is what they are obtaining, and the work was published. It's in that paper. You can look at it, and there are so many results, experimental results in the literature, which we have compared our work with and validate our work with. So there are a lot of experimental validation of our work.
Thank you, Prof. Please,
if
you have any question, please, we would like to welcome 2 or 3. If you have a question, can you raise up your hand using this platform, or you post your question on the question and answer. Yes, Mohammed Fedo. Yes, please, you can unmute yourself. Let us see your face and ask your question. Thank you.
So thank you so much, and I'd be very today I'm very glad to see all of you again, and very big congratulations to Professor Makinde. I am Mohammed Firdaus from Bangladesh.
Oh, thank you, thank you.
So how are you doing?
Yeah. I remember when I tried to see you in Bangladesh, you were in Saudi Arabia.
Yeah. Thank you so much for remembering me.
Yes.
So I have just a very quick question that what is the implication for the drug delivery system to this problem?
Yeah. What is the implication of what?
Drug delivery system, like as a injection or others, how we can use this model for the drug delivery system. I mean,
Okay. Thank you very much. That's a very interesting question. You can use this model for drug delivery. You see, that's the interesting part of mathematics. We can use it for drug delivery model. The only thing you do there is that you can look at this problem in terms of internal flow problem.
Yes.
The same model. Look at it in the form of internal flow. When you look at it in the form of internal flow, that's the flow in a tube or in a channel. Then you can now make sure that you look at it in a channel with permeable boundary.
Yes.
And then the permeability of the boundary will be affected in your boundary condition. For instance, this F we have here, F now will not be equal to 0. F here, which is based on the velocity at the normal velocity at the surface, is going to be a function, will be a value, maybe a constant suction or constant injection, depending on what you want, or time-dependent suction injection. That means you are looking at a steady flow. So that means here the normal velocity is 0. In your case, it's not going to be 0. F will not be 0. Yes. Now, when you do that, now you can look at the effect of suction and injection. That as you are increasing injection, that is, you are sucking. If this one is, suppose F0 is 1, Suppose it's 1 or it's Islam. Suppose this one is L. If F0 is L, if L is 0, that means there's no, the surface is not permeable. If L is 1, that means there is injection taking place. The fluid can be injected. If L is negative, that means fluid can be sucked out of can be suction taking place. So you can look at issue of suction and injection. And in that case, what you are sucking or injecting is nanofluid. And that means you have to surround your plate with a porous media. That porous media here will be like you are having what we call your tissue. You know, the tissue surround the arteries and the blood vessel. So you have to, this can be modified in various ways. In fact, there's a problem which I published with Dr. Nayak from India, which we also look at issue of water absorption. In that case, we are looking at internal flow with nanofluid. So we are able to look at that. In that case, we are looking also with iron oxide. Iron oxide, we are using as a magnetic field as a flow control to target the tumor cell, if there's any tumor cell. So we model things like that as well, because you can use it you can use nanoparticle also for medical applications. You are right, you can use it. But this one, I'm talking mainly of engineering application, according to
Thank you, Prof.
Yes.
Thank you, Prof.
So much.
Thank you so much.
We have 2 questions here, and because of our time, we will not be able to accommodate. We will not be able to accommodate. So, but quickly, I want to read.
Please, can you tell them to email me? Also, I'll show my email. Those who cannot, who have more questions, can email me. This is my email. Makinde@email.com. Makinde@sun.ac.za. Makinde you can use any of my email I display here. Okay, you can ask me the question quickly.
Okay, thank you. But before we go, let us quickly, we have 2 questions on this chart. Yes. Do you model viscosity in energy transfer?
Okay.
That's one. Let me read the 2 so you can answer the 2 at the same time. And the second one is that on what basis we use 2 or single phase model to study nanofluid?
Okay, thank you.
And the last one, let me quickly add this one to read. The last one is the heat transfer enhancement affected by the rate at which the nanofluid is poured on the surface? Please let us answer these 3, and we close the section. Thank you.
Okay. Now, for the first question of viscosity, the viscosity of nanofluid, I've already shown you, is model. And the viscosity of nanofluid is modeled as this. Can you see my display? Hello?
Yes, we can see, Prof.
Okay.
Yes, Prof, we can see.
Viscosity of nanofluid is this one I highlighted. This one I highlighted, viscosity of nanofluid. So you can see mu. This is the dynamic viscosity. The dynamic viscosity of nanofluid equals to viscosity of base fluid divided by 1 minus phi, raised to power 2.5. This is viscosity of nanofluid. If phi is 0, you only have base fluid. As you increase phi, the viscosity of nanofluid, dynamic viscosity increases. You can see as you are increasing phi, what you have here will be decreased, and this one will become, we are dividing. You can see what we have. So the viscosity of nanofluid increases with increase in nanoparticle percentage you put inside. So this is the model, and you can get it in the literature as well. So it's based on you can see this is based on experimental and physical observation to get all this one. The second question, under what condition do we use two phase and single phase? If you want to use single phase model. Single phase model means that you want to compare one nanoparticle to another nanoparticle and using a base fluid, or you want to use what you call hybrid nanofluid, which means you mix copper with because copper is unstable. You can take small, maybe 1% of copper plus 2% of aluminum, mix them, and so you call that one hybrid nanofluid. You can have that as well. When you want to look at the effect of nanoparticles on the base fluid in heat transfer enhancement for different nanoparticles, you can use single phase. Like the model I put for you here is for single phase. But if you want to look at in general, you know, when nanoparticle is in the fluid, that's what you call thermophoresis. With this one, the nanoparticle is spread, it's moving within the fluid, and there is a kind of interaction of nanoparticle with each other. Nanoparticles are interacting with each other, and that interaction of nanoparticle can generate heat, can generate an additional heat in the fluid. Then, also nanoparticle can be moving in random motion. You call it Brownian motion, can move around in the fluid, because their small particles can be moving around in the fluid. In that case, you are looking at two-phase. So two-phase means you want to look at the effect of internal heat generated by nanoparticle itself. And you also want to look at the effect of random motion of the particle as they are moving in the fluid, which also creates more internal generation in the fluid. That means you can use two-phase. In that case, the flow of your nanoparticle will be totally different, because you need to have concentration of nanoparticle equation, concentration equation. You also need to have the base fluid equation, which depends on momentum, energy equation will be uniform. But the nanoparticle will have a separate equation. And the temperature will be affected by the Brownian motion and thermophoresis effect, as well as concentration equation of the nanoparticle. So this one, also if you are looking at reactive nanoparticle, if nanoparticle is reacting, you can use two-phase model. In that case, you may not be able to look at the effect of one nanoparticle to the other. Otherwise, like I said, a model we have done, which was published this year with one of my students, Dr. Munaledi, where we unified the two together, whereby you can still compare and you can still have nanoparticles separate. In that case, your equation will be totally different, because you have to differentiate, your nanoparticle is no more constant. You have to incorporate all these in a logical, mathematical way that you can look at the paper, it's a different talk entirely. So that's what I can say. Now, finally, the question was saying that, what is the last question?
Is the heat transfer enhancement affected by the rate at which the nanofluid is poured on the surface?
Okay, the heat transfer enhancement is affected because the only thing is that the rate at which you put nanofluid on the surface on all surface determine the rate of heat is taken. In fact, it's common sense. If a surface is hot, if you are feeling hot, if you switch on the fan is blowing you. If the fan is blowing slowly and you are very, very hot, you are sweating, it will not take out the heat out of you quickly. But if you open the fire, you put it to the air, yes, you are there, you are this, it cools you down quickly. It takes out the heat out of you. So the same way, the rate at which you are putting nanofluid on all surface determine the rate at which heat is taken away. So increase in the flow rate, increase in the rate at which you are putting it on the surface, we increase heat transfer rate as well. If you take out heat, it will take out heat from your surface, the more you are putting it on it. So that is straightforward here.
Thank
So
you, Prof.
Enhanced by increase in the rate at which fluid is being poured to the surface. But
thank you, Prof.
Uniformly. Yeah. Thank you.
Thank you, Prof. We really appreciate you for your time that you have spent with us. Now I will transfer it back to the host. Host, back to you. Thank you.
Yeah, thank you very much, Professor Egunjumbi. And of course, thank you very much, Professor Makinde, for the very comprehensive and detailed talk on the dynamics of nanofluids and its application. We really all enjoyed it very much. And but all good things come to an end. So on behalf of all the participants, I thank you once more very, very much. And I also thank Professor Egunjumbi for his assistance in introducing you. and sharing with us your very impressive CV, and for moderating the questions as well. And also thank you to Ilya and Yazira, who acted as co-hosts and were essentially here as a plan B in case ESCOM pulls my plug and I can't host the meeting anymore. Yeah. So thank you very much again. We will upload the talk on YouTube as soon as possible, and I will share with you and with the participants the link maybe tomorrow. Yeah. Okay. So thank you very much again for your time.
Thank you very much. Thank you very much.
Thank you.
And I'm looking forward to
Thank you,
staying in touch
thank you.
with all of you. So thank you very much. Thank
Thank
you.
you.
Have a good evening. Bye.
Bye-bye.
Thank you very much.
Bye.
Thank you.
Thank
you so
you.
much.
Bye-bye.
Bye. Bye-bye.